Hi everyone, I'm Ganit Hamong Supaswat from the University of Washington. Today I'm going to present the design study of the TensorFlow Graph Visualizer, which is a project that I worked on with my colleagues at Google Research. Recently, we have seen the growth of deep learning models or multi-layer networks of calculation that bring dramatic results in many areas. For example, a network for image classification takes raw image inputs and creates higher-level features to classify the type of images, such as a cat or a dog. As this model can contain dozens of layers and millions of parameters, creating a model can be difficult. To make it easier to implement and deploy deep learning models, Google released the TensorFlow open source library. The key idea for TensorFlow is using Dataflow graph to represent computation. For example, here is a Dataflow graph for a linear model that calculates wx plus b. Nodes in TensorFlow graph can represent operations such as mathematical functions like add and multiply that you see on the left. Moreover, TensorFlow includes operations for training and debugging such as initializing value and logging data. Meanwhile, edges represent data that flows along the graph. These data are mainly tensors, which basically means multidimensional arrays. And this is why the system is called TensorFlow. The TensorFlow library is a set of high-level APIs that users can use to generate the low-level Dataflow graph. The library makes it easy to implement models that support distributed computation, various kinds of devices, and a variety of learning algorithms. However, understanding the graph structure from the code can be challenging. In practice, model developers often draw diagrams to help them understand and share high-level structure of their models. For example, you can see that this diagram mainly shows the flow between computation layers of the network. Since diagrams are critical to their work, developers want a tool to draw these diagrams automatically. Of course, the first thing to try is to use standard graph drawing tools like Graphviz. However, the graph contains hundreds of low-level operations. Many of them are bookkeeping operations such as logging and initializing values. Thus, the output layout looks pretty complex. Moreover, unlike diagrams that developers draw, the layout doesn't show the core computation flow. It's worth noting that the diagram you see here is a graph of just a linear model, which is basically TensorFlow's Hello World example. Oh well, that's Hello World. When you visualize a real-world convolution network, the layout may produce something like this, or in reverse. To help developers understand and inspect the structure of their models, we present the TensorFlow Graph Visualizer as part of the TensorFlow library. The visualizer transforms a low-level Dataflow graph into a high-level interactive diagram. In the diagram, we show an overview of the model and allows users to inspect its internal structure on demand. Let's first see a demo of the visualizer. In this demo, we will explore and learn about a Dataflow that trains a convolution network for image classification. Here we see the interface. The graph visualizer is released as a part of TensorBoard, which is an official visualization and dashboard tool that ships with TensorFlow. As you see from the tabs above, TensorBoard contains many kinds of visualizations to inspect different types of data, such as scalar, images, and distribution. In this paper, we only focus on just the graph visualization. Here, the visualization shows the Dataflow graph in two parts. The main graph on the left shows the model's core computation flow. Meanwhile, the auxiliary node section on the right shows less important operations such as error reporting, calculating gradients, and logging data. These modules are actually part of the Dataflow graph, but we extracted them to simplify the graph. This way, our main graph can show core computation flow just like when deep learning experts draw diagrams by hand. We show the data flow flowing from the bottom to the top, following a convention in deep learning literature. The bottom part processes input data. The model then produces higher level features using neural network layers. and finally make the prediction the type of images at the end. Let's zoom into the bottom part to see how this model processed input. Here, we can see many rounded rectangles, which represent modules or group of operations that can perform certain functions. Meanwhile, smaller ellipses represent individual operations. Looking at the bottom part, we can see that the model first reads input images. Since training a deep learning network requires a lot of data, the model also applies image processing to produce additional training data. While we only show the overview by default, we can expand the module to see its internal structure. Inside the processed image node, we can see operations like randomly cropping and adjusting brightness and contrast. After making more images, the model shuffles and divides these images into batches for training. Since the data become larger batches here, we can see that the output edge from the shuffle batch module becomes thicker. These image batches are then fed into the neural network layer for training. To produce high-level features from the input, the model uses two sets of convolution modules. These two modules have the same color. This means that they have identical internal structure. We can also see small icons with dash borders on the side of these modules. These dash icons represent the links to the extracted nodes. We can hold on them to highlight and click to select an extracted node like gradients. With this interaction, we can see all the layers that gradients connect to. Next, let's examine how the convolution module works internally by expanding it. Here, we can see that the module has a 2D convolution operation to combine input data with weights. The output is then added by the biases variable and passed to the ReLU or rectified linear unit, which is an activation function that converts linear inputs to nonlinear outputs. Activation functions like ReLU are one of the key reasons why neural networks can learn more complex decisions than other simple type of models. After each of the convolution layers, the model includes max pooling to downsample the layer size and perform normalization to reduce overfitting. The final part of the inference layers are the fully connected layers. Their duty is to perform high-level reasoning based on the features that the convolution layers produce. Expanding one of the fully connected layers, we can see similar weight and biases variable inside, like a convolution module. However, here, weights are applied using matrix multiplication rather than a convolution operation. After the fully connected layers, the model makes prediction for the type of images using the softmax module or multinomial logistic regression. And finally, the model calculates cross-entropy as its objective function for training. Besides the output from the softmax module, you can see that cross-entropy module takes another branch of input data, and that's basically the labels for training. With this visualization, we can see the overall structure of the network and drill down to inspect its internal structure. Next, let's look at how we transform a low-level Dataflow graph into an interactive diagram like we just shown. Given a limited time, I will show you just the key strategies, but you can read the paper to see all details. Our first strategy is to declutter the graph by extracting less important nodes. Basically, some operations in TensorFlow are common, but they do not help users distinguish different models. For example, consider a Dataflow graph for initializing a variable weight. There is a constant operation, which deep learning experts consider as parameters rather than actual operations in the graph. Similarly, the summary operations are only for logging, but behave the same for every model. Thus, we extract these operations, just make them small annotation icons that are attached to their neighbor instead. One key trick here is that we can safely extract both summaries and constants because they always connect to only one other operations in the graph. so extracting them do not change any paths between other remaining nodes. Next, to provide an overview that reflects semantic structure of the model, our second strategy is to build a hierarchical clustered graph. While this is already a common strategy that we see in visualization research, the question is how we can group the nodes to match users' mental model. Since it's possible to infer that from the graph topology, our tactic is to just let users specify hierarchy to group nodes. Basically, TensorFlow lets users give nodes a namespace just like directives in file systems. For example, user can specify a name like weight when they create a variable. Our relevant nodes will have the namespace weights as a prefix in their names. We use this namespace as a way to group nodes in the graph. While naming is optional, adding names is quite easy, so we believe that users will be willing to do it to get better visualization. Plus, most users already use node namings with non-visual debugging tools before we work on this project. So most models already have somewhat informative namespaces. After building group nodes, we then draw group edges. For example, suppose we have another module for training, and there are links from operations inside the weights module to this new train module. Instead of drawing edges directly between all visible nodes, we bundle edges between groups. This provides multiple benefits. First, we can recursively calculate the layout for each group and make layout calculation faster. Second, expanding a node only causes a minor change to the layout as the number of edges in each level of hierarchy remains the same. So it's easier for users to follow the change. Another plus point is that edge bundling also helps reduce edge crossing. While all of this seems obvious in hindsight, it took us a while to figure that edge bundling is the right thing to do. With these two strategies, we can convert this raw graph of the model, which is basically too low level to be legible, into a diagram that now shows more high-level structure. This is definitely an improvement, but the output is still quite cluttered. The question is why? A common reason that clutters most large TensorFlow graph is that some high-degree groups at the end and the beginning of the graph actually connect to many core layers. For example, we can see nodes that report errors for all the layers and nodes that calculate gradients for all layers for training. When we show this graph to deep learning experts, they actually say that these high-degree nodes are not really important because they do not help them distinguish different models. Since these unimportant nodes mess up our layout, we come back to revisit our first strategy again. Earlier, we only extract unimportant individual operations. Here, we also extract unimportant groups from the clustered graph. Basically, from this graph here, we extract the high-degree nodes at the end and the beginning of the data flow and place them on the right instead. As we have shown in the demo, we use proxy icons to represent links to extracted nodes, so users can still track these connections. If desired, users can use interaction to add extracted node back to the graph, or further extract more nodes. For example, here we add gradients back to the main graph. With these key strategies, we can produce a legible interactive diagram for TensorFlow graphs. Next, let's see some of the usage pattern and feedback. After the release of TensorFlow, we gathered feedback from many sources, including a questionnaire for internal users at Google. We also observed conversation in mailing lists and also searched for public feedback from online articles. We observed a few usage patterns. As suspected, one pattern is to inspect new model. Here are some answers when we ask users about the task they used the tool for. One answer says, understand what my code actually produced. We had layer of functions and configs. It's good to verify what we got what we intended. Another answer say, find the name of a tensor so that I could do further exploration, like seeing the evolution of a particular input. Another usage pattern is that people use screenshots from our tool to explain their models. For example, this is a screenshot from the TensorFlow official tutorial. We also see this in many third-party articles, and when people ask questions on Stack Overflow. One issue in our design is that the hierarchy in our graph would be only as good as the name that users provide. In practice, it turns out that users do add names to their graph. In fact, many users iteratively modify the names until the visualization matches their mental model, especially when they share their model with other people. We also see blog posts and video tutorials on YouTube that try to teach how to organize the graph in your code to get better visualization. As we know that developers normally do not like to change their code, the fact that they are willing to rename their nodes clearly shows the value that they get from our visualization. Finally, a common public feedback is that model visualization is a key feature that differentiates TensorFlow from other machine learning platforms. A comment on Quora says that one of the main lacking areas of almost all open source machine learning packages was the ability to visualize model and follow the computation pipeline. Meanwhile, another blog post states that we believe visualization is really fundamental to the creative process and our ability to develop better models. So, visualization tools like TensorBoard are a great step into the right direction. To summarize, I have presented the TensorFlow Graph Visualizer, a tool to help TensorFlow developers understand and inspect the structure of their models. To make a legible diagram for a low-level Dataflow graph, we build a clustered graph and extract less important nodes from the graph. Overall, our users show excitement for our tools and even ask for more ways to better understand machine learning. In this paper, we only tackle one aspect of this, which is understanding the structure of the model. But we believe that visualization can play many important roles for machine learning in many other aspects. And you can contribute to this. Our TensorBoard source code is on GitHub. This includes the new TensorBoard APIs that my colleagues at Google just released last month. This API will let you easily add new visualization tools, and with better tools, we hope we can help people understand machine learning better. And with that, I would like to thank my co-authors and my colleagues at Google and University of Washington. And I'm happy to take questions. Thank you.